Thanks a lot. Developed the remote peering Jedi, which is basically a portal in the remote peering ecosystem. So our goal was to detect and localize the remote peering IXPs. There are plenty of operational regions that appear to, be important for knowing which peer is remote and which is local. There has been a great paper in this area, but it didn't provide updated data, so we decided to do it ourselves. The main methodology is to use the huge corpus of Atlas traceroutes and calculate the altitude differences between IXP hops and the near-end hop between the far end peer and the near-end peer. Obviously, traceroutes have a lot of noise, and especially when we subtract RTTs. But the fact that Atlas has so many traceroutes and so many vantage points allows us to filter out this noise, to remove outliers. We use basically the median RTT difference over pairs of RIPE and IXPs for which we have at least 50 observations. And here are the results, beat in 10 millisecond delays. As you can see, about 60 to 80% of the peerings are local, and the ones that are definitely remote are between 10 and 20% for the different IXPs that we studied. So we studied just 5 IXPs, but just because it's a hackathon and we don't have too much time, but we plan to extend it to more IXPs. We validated against data from 3 large IXPs, for which we had boxes inside the IXPs, and we have really satisfactory results. We say that we have a true positive if both our RTTs and the RTTs from inside the IXPs are over 20 milliseconds. And for all the cases that we checked, that's pretty well accuracy. And then we try to see, whether these remote peerings are used to access some small ASs that are not available elsewhere or large content. And what we found is that most of the remote peers access large content providers through these remote peers. So interestingly, for example, some ASs in Athens or in Cyprus who are well connected in the local peering ecosystem have to go all the way to Amsterdam or Frankfurt to access Cloudflare or Twitter or Facebook, because these CDNs are not in the local ecosystem. So that's the point that I made previously. It doesn't matter just how dense is the local ecosystem, but also whether the CDN is supported. So some of the remote peers are serial remote peers, are the usual suspects. So you see them in every of the IXPs that we studied. They were there, and it appears that when they start doing it, it's very simple to do it to many IXPs instead of just some specific ones. So it appears that they don't target a specific ecosystem, but they try to extend their peering reach as far as they can, and they do it aggressively. But this has strong implications on the actual multi-homing resilience for these AES. So they may appear that have a lot of peering diversity and resilience, but in reality they're just remote peering from the same point that's far away. So also this work gives some insights on how to interpret the facility information in PeeringDB. We checked for how many of the remote peers that we found, they record facility presence that is local to the IXP, and we have about 16 to 25% of them claiming they have a local presence, which obviously means different things for different operators. They do it voluntarily and manually. So either they indicate not exactly physical, presence, but the ability to set up connections through this facility, or it's a mistake, or they do it even in purpose to make themselves more attractive as peers and initiate contacts. So maybe that's a point that these automated tools can take into consideration, that the data in PNDB may be manipulated in order to appear more attractive. So it may be possible to game these tools to boost their Tinder profile. So that's the point that I guess there is noise that will affect these APIs. So now we have the question: where are the remote peers? So far we solved the problems of whether a peer is remote or not. Now where are they? We used some available geolocation techniques that are considered accurate, like Open IP Map and DNS-based geolocation. But this can geolocate only a subset of the IPs. So for the rest, we either had to fall back to some inaccurate techniques like geolocation database. There are some very high complex techniques like trial iterations, which is no readily available implementation, and the hackathon was too solid for us to do it. But we implemented something new, completely new over the Atlas platform, which is the presence-informed RTT-based geolocation. So what we do, what we say here, what we claim is that if we reduce the problem space of geolocation, we can improve the accuracy without increasing the complexity a lot. So the key intuition is that a target IP that we want to geolocate will be in an area where the AES has presence and not just anywhere in the world. So we check PNDB for to collect the presence of AES in all the possible cities. We take the Atlas probes in these cities that the AES claim to have presence, and we run pings, and we select a city with the lowest ping if the ping is low enough to indicate that it's local, let's say less than 5 milliseconds. So here's an example. This is an AES that we determined to be remote in decades. From PNDB we found that it has possible presence in 10 cities. We selected 5 probes from each city, and we ran the pings, we got the RTTs. We implemented this using Cousteau and the streaming API. And then we took the minimum RTTs from the probe in the city, we grouped them, we took the average, and we found that it is in Riga, in Latvia. And not in, so you can see here the delays in Germany, which is remote peer are pretty high. So it's obviously a remote peer, and apparently in Latvia, in Riga. Okay, so now we developed a portal where someone can go and, someone can go and check for a given XP the remote peers where they are, and Petros developed it, so we give more detail.
You kind of run out of time, but we'll give you some extra time.
Yes, sure. Yeah, it will be quick.
Okay, there is a legend which displays the IXP that we started, and you can select the IXP, like in some BAM sheets, and you can see all the remote peers that we found and geolocate. And for the case study of Athens, we found 2 remote peers that also exist on the TKIX IXP. It's exactly the same afternoon systems. And we studied an internet exchange point in the US, in Los Angeles, and we found remote peering from Pacific.
Yeah. So you see the difference in remote peer, and So that's also someone can check the portal if they want to see who is remote peering. Maybe they want to, do the remote peering selection accordingly. It's a nice way to really conceptualize the global scale of what is supposed to be local. And it's public, and we will extend it beyond these IXPs to the entire thing. Thank you very much.
Thank you, beautiful. First question, is it real data?
It's real data, yeah. So all this data are real. We collected, first of all, the intuition is that if we want to keep an updated data set of remote peers, it's a good idea to use the corpus of the Atlas trace routes that it's really large. We get continuously more trace routes that tend to cross many IXPs. There are projects that already target IXPs, so we have data. It's a matter of exploiting them. So we took the data for the past month, and we parsed and extracted the peers and everything, added to it. So it's real data.
So first of all, I mean, this is a great presentation. How do you see this? I mean, I can see the value for research purposes. I'll use a microphone because I'm very loud. So I can see the value for research purposes. How do you envision, so I've got two questions. One of this is, how do you envision this is going to help peering managers?
Yeah.
So that's question number one. Second question is, how can I, as a peering coordinator or a network manager, integrate this extra knowledge into my routing information so I can actually make smarter decisions?
Right. So it's basically, there are, first of all, there was a very interesting presentation in RIPE 65, the great remote peering debate, which answers some of these points that boil down to the fact that sometimes it may be good, some operators may want to avoid remote peers, but there's not enough transparency always to know who is remote and to know where the remote peer is and what is the latency that they experience. So through this portal we provide all this information. We had feedback that some IXPs have developed similar tools for their members that are not public. And so obviously this has direct operational interest for since IXPs already considered this as a way to inform the peering decisions. Also, during the presentation, I made a few points. First of all, about what can we learn for these remote peers, the peering information that they provide, whether it is accurate or how it should be interpreted. So I think it gives a lot of insights, not just for the remote peer itself, but also for the broader presence of an IXP and the information they provide. And since we move toward more automated peering coordination, it may be good to take this data with a grain of salt, and it may be good to cross-validate it with some, measurements, actual, measurements from Atlas or other applications that may not be public necessarily.
Thank you. Any more questions? No, thanks.
So then we have Barry, or all of you.